Hi, this is Fangyu. I'm a PhD student in the Department of Electrical Engineering and Computer Sciences at UC Berkeley. Today, I'm going to talk about motion planning for autonomous vehicles on understructured roads using a new data structure named stacked reservation grids. We all know that industry leaders such as Waymo and Uber have already solved autonomous driving in relatively well-structured environments, for example, driving on a highway in free flow. However, as highways become more and more crowded, the order or the structure of the roads will become more and more chaotic. This makes safe and efficient driving very, very hard. This also applies to urban streets. We have not yet solved the driving problem in those understructured road environments, which are also very common in many developing countries. If we look at a standard perception, planning, and control pipeline in a standard autonomous vehicle system, we will find out that most of the difficulties of driving in understructured environments come from tracking and prediction. To address the challenges, we propose a new data structure named Stacked Reservation Grid, or SRG. Introduction of SRG removes the need of precise tracking and prediction. We argue that computing SRG from perception is a natural extension to current deep learning-based computer vision methods. We also describe how SRG can be used out of the box with model predictive control. To begin with, let me motivate the definition of SRG using occupancy grid. We know that occupancy grid is a data structure that encodes spatial information on a 2D lattice. If one needs to describe a dynamic environment, he or she will need to use a stack of occupancy grids by first discretizing the time and then generate an occupancy grid at every time step. However, this method does not scale well with long time horizon as well as small time step. To resolve the problem, we propose a new data structure named the reservation grid. In a reservation grid, we only store the arrival and departure times of the object at every lattice element. This new representation works efficiently with arbitrarily long time horizon and arbitrarily small time step. In a multi-agent environment, if we generate a reservation grid for each agent and stack them together, we obtain a SRG, or stacked reservation grid. Note that by taking the mean across the arrival channels and the max across the departure channels, we will be able to compress a multi-channel SRG into a double-channel compressed SRG. Compressed SRG can work very efficiently with both perception and planning modules. First, it finds natural integration into any modern computer vision neural networks through a tensor-to-tensor autoencoder. It is also easy to be used for planning, acting as a part of the non-collision constraints in a standard MPC formulation. If we compare SRG with other common representations, we will find that SRG provides a good trade-off for navigation tasks in understructured environments. On the level of system architecture, the proposal of SRG enables an alternative design that trades between modularity and homogeneity. As the next step, we are working on validating the concept of SRG using an empirical dataset called the Berkeley Deep Drive Drawn dataset, or the B3D dataset. The B3D dataset contains a variety of understructured road environments, such as unsignalized intersections, unsignalized roundabouts, congested highways, and congested highways with bottlenecks. We are planning to release our work this summer, along with the dataset. If you are interested in getting a preview of our dataset or have any questions, feel free to email me. Thank you.